In our previous video using Microsoft Excel for statistics, we looked at the Pearson chi-square test for independence. Now we had two binary categorical variables. We wanted to test whether they had an association, and under the null hypothesis, there's no association between those two variables. This time round, we are going to have one binary categorical variable, but the other's multinomial. And the thing about the Pearson's chi-square test is neither of them are restricted to be binary. We can have two multinomial categorical variables to conduct a Pearson's chi-square test. And here we are in Excel. We see our two variables. They are both categorical, but in this instance, they are not both binary. Let's copy our data. I'm going to click in any one of the cells with values. I'm going to hold down Control Command, hit A, Control or Command, and hit C to copy. I see my marching ants. I'm going to open a new sheet. I'm going to say paste values. Let's do one more sheet and again paste values. I'm going to go to this first new sheet. I'm going to call it copy. And remember, this is just part of my normal workflow. I always want a copy of the data that I can change if needed, but I also want that original that I never touch. Let's go to the second sheet. And this one I'm going to call Pearson because we're going to do a Pearson chi-square test, or a chi-square test for independence, or a chi-square test for association. So I'll click in any one of my cells and I'm going to go to Insert, make this a table. My table does have headers. In that first row, we see the names of the two variables. So I'm going to click OK. And now it's a table. Both are categorical variables. All I can do is frequency. So let's create a pivot table. Click in any one of the cells. I'm going to go to Insert. I'm going to go to Pivot Table. My Select a Table or Range is already done for me because I was in one of those cells. I'm just going to put it somewhere. Let's put it in an existing sheet. I'm going to hit my selection button. I'll go up to E1. Let's put it right there. Expand again and hit OK. Now, as with the previous video, we're going to see our two variables there. I'm going to drag exposure down to rows, and I'm going to drag outcome down to columns, and I'm going to click and drag any one of those two. Click, hold, drag any one of those into values, and I have my contingency table. And look at this. As far as my exposure variable is concerned, in this instance, it is binary. It's exposure, non-exposure. Now, for this Pearson's chi-square test, it need not be binary. When I look at my outcome variable, I see three levels: improve, stable, and worse. So I have a binary variable and a multinomial variable. Now do watch the previous video. Remember there we had two binary variables for the measures of association, but also for the Pearson's chi-square test. The hypothesis test, called the Pearson's chi-square test though, is not limited to two binary variables. I can have two multinomial variables, and in our example here we have a binary and a multinomial variable. That gives us a contingency table that is 2 by 3, 2 rows and 3 columns. So in other words, 6 cells. And as I say, you can have more than that. We just have to watch out though. We need at least 80% of these values to have 5 or more values in them. All the other assumptions for Pearson's chi-square test would have to hold. These values, all these individuals, these subjects, they have to be independent of each other. This is a large enough data set. We see 632 people, and we certainly have a big enough frequency for each of these joint frequencies. In this video, let's calculate the expected values. We'll do that first, and remember we're going to go cell by cell, and for each one of those cells it's its row total times its column total divided by the sum total. Under the null hypothesis, this joint probability must equal the product of those individual probabilities. So I'm going to say equal, so let's start with this 151. Its row total is 300 times its column total is 194 divided by the sum total is 623, and I get under the null hypothesis I would expect 92% if these two variables, exposure and outcome, are indeed independent of each other. If I just look at exposure and improve for the two levels, that joint probability there must equal the product of the two probabilities. Let's move to this 50. I'm going to say right there, I'm going to say equals the row total times the 50, its column total is 138 divided by sum total. Next one equals the row total for 100 is 300 multiplied by its column total is 300 as well, divided by sum total. And let's do the other three cells very quickly. Equals row total times column total divided by sum total. Next one equals the 88 there. Its row total is 332 times its column total is 132 divided by sum total. And then finally for the 200, that's equal the 200, its row total is 332 times its column total is 300 divided by sum total. So under the null hypothesis, this is what I would expect. Now let's decide on the following value and calculate the other two. So for the alpha value, let's choose 0.05. The degrees of freedom is that's going to equal, I'm going to say the number of rows, that's 2 rows minus 1, times the number of columns, that's 3 minus 1. So 2 minus 1 times 3 minus 1, and that 2 comes from my exposure variable was binary, it had 2 levels, and the 3 comes from the fact that my outcome variable had 3 levels. And so we have 2 degrees of freedom. Let's calculate the critical value for our x squared statistic. So that's going to equal chi-square.inv, there we go. My probability is going to be 1 minus my alpha value, comma, my degrees of freedom is 2, close my parentheses, and we see a critical value of 5.99. Now let's calculate our x squared statistic. Now remember, to do that, we use this formula. It's always observed minus expected squared divided by expected. So let's go cell by cell. I'm going to put it right here. I'm going to say equal, open parentheses. So there's the observed 150 minus the expected is 92. Close that subtraction, square that, close the parentheses for the numerator, divide by expected. And there we see 36.41. Let's go to cell in the first row, second column. That equals open parentheses. Observed is 50 minus expected 65.51, so it's this corresponding cell. Close my parentheses, that's for the subtraction. Square that, close the parentheses for the numerator, divided by the denominator is still the expected. So clicking on the 65.51 again, and I see my second value. Let's go for the third one, a bit quicker, equals open parentheses, observed minus expected. Close parentheses, square that, close parentheses, divide by expected. Let's now go to row 2, column 1, equals open parentheses, observed minus expected, close parentheses, square that, close parentheses, divide by expected. And let's do the other two. Now let's calculate our x squared statistic. And that's going to be the sum of all these 6 values. I'm just going to drag over all of them. Close my parentheses, and we see a very large x squared statistic. That is quite large, and it is much larger than our critical value of 5.99. We are really in the zone of rejection. One of the 5% least probable x squared values we would get under the null hypothesis. All those possible x squared values in that pattern that is a chi-square distribution with 2 degrees of freedom, that probability density function, so that is very large. And we reject this null hypothesis. Let's do a p-value for that. P-value. Now remember, that must be 1 minus, so we can say equal 1 minus chi-sq.dist. Our x value that we want there is the x squared statistic, comma, the degrees of freedom would be 2, comma, cumulative would be true, close parentheses, and we see 0. There is so many zeros after the decimal place, Excel has just decided to put 0. That is a very small probability of this outcome that we had. And so by the critical value approach or by the p-value approach, we, in both cases, you should get exactly the same conclusion. We reject the null hypothesis. Remember, the null hypothesis is that these two variables are not associated with each other, and then the alternative hypothesis that they are. So in this case, we would say that exposure and outcome, those two variables are associated with each other. Alternative, we would say they are not independent, or we would say they are dependent. There's just so many words that you can use here. And there we have the Pearson's chi-square test.